Hi there, you're with Mr. Laurie, and this is part 12 of the linear and nonlinear relationships topic. Last lesson, we were looking at further polynomials. That was lesson 11. Remember, polynomials are curves that have a power such as 2 or 3, that's our parabolas and cubics, but further polynomials have higher powers like 4, 5, 6 and so on. Before we move on to intersection of graphs, that'll be next lesson, we're actually going to go back and look at some cubics. And not just our standard cubic, y equals x cubed, but we're going to look at cubics in a different form. Before we get started though, we're going to jump over to Desmos, have a look at parabolas and cubics. So starting with parabolas, you might remember that parabolas in general form can be represented by y equals ax squared plus bx plus c, where a, b and c are any integers. If, for example, we had a set to 1 and b and c set to 0, that would just give us the standard parabola y equals x squared, like that. However, we can adjust a, b and c to be any values we want. We might keep a as 1, but set b to be something else, like 2. And you can see how the parabola is changing as we change these values. And we can also set c to be any value that we like, right? Moving it, that's the constant value, so it moves our parabola up and down. Let's set ours to be -3. Looking at this graph, we can see that it cuts the intercepts, or the x-axis, at 2 spots, -3, 0 and 1, 0. That's not readily apparent when it's in this general form, y equals x squared plus 2x minus 3. However, that is easier to see when we factorize a quadratic, and so we would turn y equals x squared plus 2x minus 3 into this form, y equals x minus 1 multiplied by x plus 3. And you can see that it's the exact same parabola, okay, whether it's this one here in purple or this one here in red. Exact same parabola, because we've just factorized the first one. When it's in this factorized form, if we set x minus 1 equal to 0, we get x equals 1, that's this point here. Or we can set x plus 3 equal to 0, and we would get x equals -3. That's our intercept here. We know that the intercepts are -3 and 1, like I've just pointed out, but how do we know whether our parabola is a happy parabola, smiley face, or an upside down parabola, a frowny face? Well, that's because this is a positive equation. If it was a negative equation, we would get our upside down version. Okay, so the red one here is our positive at the moment, because we have a equals positive 1. Okay, but let's take that one away. We'll just focus on the purple one. So if we have a negative parabola, we know it goes like this. If it's a positive parabola, it goes like this. But notice that the x-intercepts, 1 and -3, stay exactly the same. Well, just like we can take a parabola from this general form and write it in terms of its intercepts, we can do the exact same thing with cubics. So let's go back to our notes now, and we'll write a few things down. So the standard cubic is y equals x cubed. And we know that it looks a little something like this. Just a quick sketch of the y equals x cubed graph. However, just like parabolas, cubics can also be written in terms of their intercepts. A cubic that has x-intercepts of r, s and t would look like this. There could be some coefficient out the front, Remember, that just adjusts how steep the graph is. But if the intercepts are r, we would have an x minus r. S would give us an x minus s. And some other x-intercept t would give us an x minus t. For example, putting some numbers in, a cubic could look something like this. 3 is the coefficient out the front. We might have x minus 2 multiplied by x plus 1 multiplied by x minus 4. So see, it's very similar set out to parabolas that you've seen before, but we've got this extra term on the end. And that makes sense because a cubic has an extra power. There's an extra x in there. What would the x-intercepts of this cubic be? Well, remember that for x-intercepts, y is 0. So we're setting y equal to 0. If this expression here is equal to 0, then any one of these brackets can be set to 0. So we could have x minus 2 equal to 0, or we could have x plus 1 equal to 0, or we could have x minus 4 equal to 0. Solving each of these, and we get x equals 2, x equals negative 1, and x equals 4. So if we were to graph this, we know that we could plot these x-intercepts before we start. So here's our y and x-axes. Let's put a few scale points down. And let's plot our 3 x-intercepts that we've come up with. Negative 1, 2, and 4. If this was a parabola, if we were talking about parabolas, once we'd plotted the x-intercepts, we know that a positive parabola is a happy face and a negative parabola is a frowny face. But what are we going to do with a cubic? See, there's one of two ways this cubic could go. It could look a little something like this. Or perhaps it looks a little something like this. How do we know which way this cubic goes? Well, testing points is one option. But I'd like to draw your attention to this fact. If we look at the very right intercept, so in this case it was x equals 4, that was the furthest intercept to the right. If we start on the right hand side of that intercept, a positive cubic will start above the x-axis, so where this blue line is, whereas a negative cubic will start below the x-axis. That's our easiest way for determining which way or what shape our cubic will have. So a positive cubic will start above the x-axis, and if we know that the 3 intercepts are here, here, and here, it will look a little something like this. It will start above the x-axis over to the right, and then cut through our 3 x-intercepts. On the other hand, a negative cubic will start below the x-axis when we start from the right hand side. So if we had those same x-intercepts at these 3 points, but it was a negative cubic, we would start down below the x-axis on the right hand side, and our cubic would then cut through these intercepts like so. Okay, so this was our positive cubic, and this is the shape of our negative cubic. So going back to our introductory example, all the x terms are positive. So when they get multiplied together, we'll have a positive x cubed, and the 3 out the front is positive. So this is a positive cubic. And so our graph down the bottom here, the true graph, is going to be represented by which line, the red or the blue? It's going to be represented by this blue line, because we start positive over on the right hand side. Okay, so that is the shape of the graph in this particular example. Now so far we've looked at the 3 roots of a cubic being individual values, but what about if we have double roots? Now what do I mean by this? Let's write down an example of an equation. Y equals x minus 3 and then another x minus 3 and an x plus 1. Because we've got x minus 3 times itself, this might more commonly be written as x minus 3 squared times x plus 1. When we find the x-intercepts of this cubic, we would see that the x-intercepts are 3 and negative 1. So we only have 2 x-intercepts, even though we know that this is a cubic graph. In general, when we're looking at a cubic, if it's a single root, it will cut the x-axis, whereas a double root just touches the x-axis. So in this particular case, we have roots at negative 1 and 3. So let's put them on first. Okay, so one here, one here. But at 3, this is what we would call a double root. So this one here is a double root. Whereas this one over here is just a single root. Now this is a positive cubic once again, so we'll be starting over in this top right hand side. However, when we come down to the x equals 3 point, we're not going to cut through, but rather just touch the x-axis before looping back up and then turning around and cutting through this one and then heading off down there. So a single root cuts the x-axis like we've seen previously, whereas a double root just touches the x-axis. You might do a few examples now. Example 1, we're going to sketch y equals 2 outside of x minus 1 times x minus 4 times x plus 2. When we set x minus 1 equal to 0, we get an x-intercept of 1. When we set x minus 4 equal to 0, we get an x-intercept of 4. And our third x-intercept, when we set x plus 2 equal to 0, is x equals negative 2. So they are our 3 x-intercepts that we can mark down to start this sketch. Remember, when we're sketching, we just need to get the basic shape and the key points of our graph. It doesn't have to be super detailed. So setting up a scale. just on our x-axis. Alright, let's mark down those three x-intercepts. X equals 1, x equals 4, and x equals -2. Now to the shape and direction of our cubic. Because it's a positive cubic, over on the right hand side, we're going to start above the x-axis. So our graph will start up here, come down and around, cut through 1, turn around again, and cut through -2 before heading off for infinity. Be sure to put the arrows on the end of your graph to show that it continues in that direction. So we've marked our three x-intercepts, -2, 1, and 4, but we also have this y-intercept here, which it might be handy to mark down. For y-intercepts, remember that anywhere along the y-axis, the x-coordinate is 0. So in our original equation, let's set x to 0. So y equals 2 lots of 0 minus 1 is -1, 0 minus 4 is -4, and 0 plus 2 is 2. Working that out, 2 times -1 times -4, so those two negatives make a positive, times 2 again gives us a value of 16. So this here is 16. Now we can see that my y-axis does not have the same scale as my x-axis. It would have to be a lot higher if it was, but that's okay. This is just a sketch. Alright, so as long as we get the basic shape right and then we label our key points, we're all good. Alright, let's have a look at example 2. Sketch y equals -x minus 1 squared times x plus 2. So, setting our first lot of brackets equal to 0, x minus 1 equals to 0 gives us x equals 1, and x plus 2 equal to 0 gives us x equals -2. So there only appears to be two x-intercepts, but this first one, x equals 1, is a double root. So let's draw up our axes, and we'll mark down those two x-intercepts. The first one is at x equals 1, and the second one is at x equals -2. Remember, at the double root at x equals 1, our graph will just touch the x-axis rather than cutting through it. But which direction do we start in? Well, this is a negative cubic because of this negative out the front here. So, starting from the right hand side, we're going to start from below the x-axis. However, we'll just touch the x-axis and turn around before cutting through -2. Once again, we've got the shape and we've got the x-intercepts, but what about this y-intercept here? Let's set x equal to 0 in our original equation. We have y equals negative, then in the first lot of brackets, 0 take away 1 is -1. But remember, this is squared, so -1 is squared. In the second lot of brackets, we have 0 plus 2, which is 2. -1 squared is +1, but we still have this negative out the front. So our final answer when we work this out is -2. And judging by our graph, it makes sense that we get a negative answer for our y-intercept. With those two examples done, that concludes our lesson on cubics that are written in terms of their intercepts. Thanks for watching.